I'm Catherine Hambleton from NASA's Office of Communications. We're here at the Flight Robotics Laboratory flat floor at Marshall Space Flight Center to provide you an exciting update about the first launch of the Space Launch System rocket and the Orion spacecraft, and the science and technology that we'll be sending along to find out more about deep space. We will have two parts to today's program. First, we'll open with Marshall Center Director Todd May and NASA Deputy Administrator David Newman. Then I will announce the panel of representatives here on the stage to provide more details about today's announcement. In the second part of the program, we'll give you a behind-the-scenes look at some cool hardware that will be on that first flight with a mission of its own to learn more about an asteroid and test its solar sail technology. There will be a question and answer period at the end of each part of the program for media representatives present in the room, as well as those on the phone and following us on social media. For those joining us online, you can ask questions using the hashtag AskNASA. At the conclusion of the panel's remarks, I'll provide additional details about the question and answer period. And now, to start us off with a few words, Center Director Todd May.
Hey, thank you. It's good to have you all here today, and good to see all the folks that want to learn about the capability that we're bringing to the agency. Thank you for joining us today. This is a briefing to announce secondary payloads for the first launch of the Space Launch System, the largest and most powerful rocket ever built. You're about to learn about exciting capabilities of SLS above and beyond its primary mission. And that primary mission is to launch the Orion spacecraft into space beyond the moon and onto Mars. It's the only rocket and spacecraft equipped to send humans and supplies required for deep space exploration. The first mission will be called Exploration Mission Number 1, and it'll be a proving ground mission, whose goal is to demonstrate the integrated performance of the SLS and Orion before we put crews on it for the first crewed flight. Because of the robust capability of the Space Launch System, we have a unique opportunity to transport small spacecraft and technology experiments on board the very same mission. Today you're going to hear about 13 small satellites that we're going to send out into space on this mission with the extra capability we have beyond that needed to launch Orion beyond the moon. Here at Marshall, we manage the Space Launch System program, and we're tasked with integrating these payloads into the vehicle for the agency. We're also privileged to have two of the principal investigators, the Lunar Flashlight and the Near-Earth Asteroid Scout mission, and to manage one of those missions here at the center. All of the data from these missions and these experiments will be used to help us on our journey to Mars. And now I'd like to introduce you to Dr. David Newman, our Deputy Administrator, and someone who is very familiar with innovation and technology in her own right. She's in Washington, D.C., and she will tell you more about the importance of transporting these small satellites on the SLS and how the S&T, the science and technology gleaned from these missions, will advance us on our journey to Mars. Please help me in welcoming Dr. David Newman.
Thank you. Morning, everyone. And first, my honor and congratulations to Director Todd May, Marshall Space Flight Center's 13th director. Todd, throughout your entire career, you have consistently and persistently helped us advance exploration. So we're so proud of you and really look forward to working with you in this new role as director. It's great to be here in Rocket City. I love coming back to Huntsville. Today, we get to highlight another step on our journey to Mars and our continued progress toward that first flight of SLS, the Space Launch System. In our journey to Mars, there are many facets, and it's really important to note that this Team Marshall is right at the core. We say it goes through, the path to Mars goes right through Huntsville and right through Marshall. So this amazing work on the development and testing of SLS. And this first mission, as we know, is going to be about a little bit more than propulsion. It's also going to be about what science, what technology can we do, and that's why we're all here today for this very exciting announcement. Cubesats, 6 units, like a shoebox. They're really at the cutting edge of technology. They used to just be a dream. Today they're developed and they're efficient, they're cost effective. They're really showing us how to do exploration in a new way. During Exploration Mission 1, EM1 as we call it, NASA will expand our science and exploration capabilities by sending 13 of these small Cubesat class payloads into orbit. And the design and the advanced technology that we'll be flying is really setting the stage for our future human exploration missions. These 13 Cubesats that will fly, they're called secondary payloads, and they're going to showcase, they're really at the intersection. I like to think of it as being the synergy of what we can do scientifically and technology. So this is where it's a really good look of how much science and technology we can cram into that very small package, and you're going to be amazed when you hear all the details coming up. But it really is helping us advance our journey. SLS and their Orion spacecraft, they're going to take people further than we've ever taken people in human history. Further than we've ever been in over 4 decades out into deep space and onward to Mars. So these technology missions in deep space are really something to pause, reflect on. We're not just talking about it, we're doing it, and it's starting right here. SLS is designed, and it has a flexible and evolvable architecture that's really important. The crew and cargo missions, they enable very large science experiments, technology demonstrations for exploring the universe, so thinking way, way out, and also they carry smaller secondary payloads and capabilities so we can test things out on these Cubesats. So as an aerospace engineer myself, that's really important. In systems engineering, thinking about the flexibility, how can we carry all kinds of different payloads from small to large, all kinds of science, all kinds of technology. That's really a new way to look at evolvable, flexible space systems. That's really what SLS demonstrates. EM1, Exploration Mission 1, is a proving ground mission, as Todd mentioned. What does that mean? Well, we're going out to deep space. This orbit leaves Earth. It goes to lunar orbit, past lunar orbit. The view from there is pretty spectacular when we look back on our own spaceship, Earth. So these Cubesats that were chosen have the ability, and they really have amazing capabilities on board. You're going to hear more about the key information, and it really increases effectiveness and improves the design of subsequent robotic and human missions. So these are precursors, but they do their own science in their own right. And perhaps one of the most exciting things to me is what's going to be called the NASA's Cube Quest Challenge. Those ones haven't flown yet because the innovators are still working on them today. They're going to help test out spacecraft propulsion and communication techniques. So they're still in competition, working on those. So we'll just keep rolling out these great announcements. So that's a really amazing challenge that you're going to hear more about. So this is a very exciting opportunity. It's an incredible announcement. I'm so glad to be here in person with everyone. I look forward to the continued progress of SLS and the wonderful news like today's, which is helping us really bring to life, make it tangible, to celebrate the developments of exploration and to highlight the future missions that are happening here today at the Marshall Space Flight Center. Thank you all.
Thank you, Dr. Newman. Joining us here on the stage today to talk with us more about our deep space exploration journey and exciting science and technology along for the ride are Mr. Bill Hill, Deputy Associate Administrator for Exploration Systems Development at NASA Headquarters, Mr. Michael Seablum, Chief Technologist for the Science Mission Directorate at NASA Headquarters, Mr. Jim Cockrell, CubeQuest Program Administrator at Ames Research Center, and Dr. Jitendra Joshi, Technology Integration Lead for the Advanced Exploration Systems Division at NASA Headquarters. At this time, we'll begin with our first panel member, Mr. Bill Hill.
Good morning, and thanks for being here with us to celebrate this this great endeavor we're about to get on, the journey to Mars. This is going to be part of it, our Cubesats. Exploration Systems Development is making great progress toward our first test flight in 2018, the Exploration Mission 1. The Space Launch System, Orion, and the ground systems that support both pre-launch and recovery are making great progress. In 2015, we saw the completion of seven planned engine tests at Stennis. We saw a solid rocket booster test that was very successful. We have another one this year coming up in May. We got the Vertical Assembly Center at MAF, the largest single weld tool in the universe, up and running and working, and we're making great progress on our confidence welds as well as soon to be welding the Exploration Mission 1 hardware. We also saw the completion of the Orion pressure vessel, and we saw that delivered from MAF to KSC yesterday, and we'll begin very soon outfitting that. But today we're here to talk about the Cubesats that we're planning to fly and deploy on EM1. As Dr. Newman said, these are secondary payloads. Our primary mission, obviously, is the flight test, integrated flight test of Orion and the Space Launch System, as well as the ground systems that support pre-launch and recovery. We have selected 13 Cubesats for this mission. We could select up to 17. We've got those positions. We started with 11 and decided we had sufficient resources to do 13. Working both within NASA and with our international partners, as well as we made offers to the intelligence community, and because of our trajectory toward the moon, they declined that offer. Exploration Systems Development, internal to my organization, conducted a feasibility study of all the candidates, and we had more than 13. Proposed, looking at the mission profile, and they down-selected to these 13, presented them to me for approval, which I did, and then we took them to our agency flight planning board recently and had them approved for flight. 10 of the Cubesats were selected from in-house through competitive processes, such as the CubeQuest challenge and the Next Step broad area announcement. 3 are international Cubesats that we're looking at and in negotiations today to get those on board. We won't be talking about those today. We'll find a future occasion to celebrate those and announce those. But each of these Cubesats are complementary to our objectives for human exploration and objectives for EM1, kind of at a smaller level. And they, as Dr. Newman said, press technology and science and provide us a capability that we might not otherwise have. Exploration drives science, and science drives exploration and technology. So with that, I'm going to pass it on to Jim.
Hi. Science Mission Directorate is really excited to be part of this opportunity to fly Cubesats on the SLS. Today's Cubesats represent a culmination of over 10 years of development, mostly by the academic community. The early missions that occurred back in the 2004-2005 timeframe were largely for educational purposes, and when there was a science payload, they tended to be somewhat pedestrian in nature. Today, we have a convergence of the technology for miniaturization of instruments and also advancements in platform capabilities that have come together that have really enabled us to have a new science platform. Cubesats and other types of small satellites offer new opportunities for researchers to place their instruments in space. And we're not talking about investigators just at the large, more familiar institutions. We're really talking about new investigators from universities that have never before done business with NASA. We're seeing this now in our most recent solicitations. So it's great to see a very young and diverse set of researchers involved. It really does inspire the next generation. So in the Science Mission Directorate, we plan to continue to invest in technologies for miniaturization of science instruments through our dozen or so technology programs. And also, we will encourage the collection of scientific data from these observing platforms through our research solicitations. So today, I just wanted to introduce two of our, or the two science payloads that will fly on the SLS. The first is the Lunar Hydrogen Mapper, or Lunar HMAP, and the other is the Cubesat mission for science for investigating solar particles. The first mission is Lunar HMAP. There's an image of it now on your screen. If we could go back to the first image, please. That's it. So you can see that this is the entire spacecraft. This is Lunar HMAP, the size of a shoebox, with the rather photogenic PI. That's Craig Hardgrove. The purpose of the mission is to characterize the distribution of hydrogen that exists in the permanent shadows of the south pole of the moon, in the craters and on the plains. Because of the investments we've made in technology, this mission, which will carry a neutron spectrometer and also an imager, will give us unprecedented horizontal resolution of the distribution of hydrogen. Roughly 7.5 kilometers per pixel is what we're expecting. And if you could go to the next chart, you'll see the planned orbits in the red. There's an advanced propulsion system that has a dozen or so miniature thrusters to provide attitude control. This will give us more than 140 orbits over its planned 60-day life cycle. There'll be a Vertex 5 field programmable gate array processor for the science data processing, and they're going to be using JPL's Iris X-band radio for downlink communications. So it really is a convergence of a lot of technologies. The neutron spectrometer was miniaturized, and these platform technologies to provide the communications and the thermal control, all of these things have come together to give us a very cost-effective science mission. Okay, the next mission on the next chart is Cusp. This is also a 6U Cubesat, so two is roughly the size of a shoebox. Cusp will study this is a heliophysics mission. This will study the characteristics of solar and interplanetary particles, and will also contribute to our knowledge of space weather forecasting by examining superthermal particles and to better understand their role in contributing to geomagnetic storms. This mission contains 3 instruments: the superthermal ion spectrograph and the miniaturized electron-proton telescope. These 2 instruments will characterize the energy levels of these particles at different portions of the energy spectrum, and also a vector helium magnetometer to help characterize the magnetic fields. So both of these are highly cost-effective scientific missions that are enabled by our investments in technology, and also by the contributions from our academic community. Thank you.
Good morning. I have the privilege of administering the CubeQuest Challenge. CubeQuest Challenge is STMD Centennial Challenge Program's first ever in-space competition for prizes. The contest is open to any non-government US-based team that chooses to enter at no cost. The teams will compete through a series of events on the ground that we call ground tournaments, and the team selected at Ground Tournament 4 will be offered a free ride on the EM1 launch. There are 3 slots that have been allocated to the CubeQuest Challenge. The 2 years of events that leading up to the launch are called ground tournaments. Coincidentally, Ground Tournament 2 registration deadline is this Friday, February 5th. During the ground tournaments, the teams are judged by a panel of judges for technical excellence and compliance with the challenge rules and requirements. There are 4 of these ground tournament events leading up to the down select for the 3 that will be chosen to launch. After launch, the fun doesn't end there. The Cubesats, once dispensed in a translunar injection trajectory, will go on to compete for in-space prizes. And this is the first ever in-space challenge offered by NASA. Those teams that elect to enter lunar orbit, if they successfully achieve lunar orbit, win a share of $1.5 million prize. Some teams, and if you go to the next slide, rather than going to lunar orbit, they can proceed on to a range from Earth of 4 million kilometers. Now that's more than 10 times the distance between the Earth and the Moon. We call this the deep space derby, going to 4 million kilometers, as opposed to getting into lunar orbit, which we call the lunar derby. Now, whether in the lunar derby or the deep space derby, from lunar orbit or from 4 million kilometers, the teams then proceed to compete for accomplishments in communications achievements and for longevity. The last Cubesat we hear from will also win a prize. There's a total of $5 million prizes that will be awarded in the CubeQuest Challenge. And in order to win those prizes, our teams are going to have to demonstrate advancements in propulsion's capabilities, communications technology, and in order to navigate around the Moon or distances of 4 million kilometers, these little Cubesats that are briefcase-sized are going to have to advance their capabilities in autonomous operations and power management and navigation beyond the constraints of low Earth orbit. These are the kinds of capabilities that Cubesats are going to need as NASA proceeds on its journey to Mars. The capabilities that our teams are advancing, some teams are proposing doing laser communications from long distances. Other teams are advancing electric propulsion, perhaps solar sails, new kinds of electric propulsion, new kinds of chemical propulsion. These are the kinds of capabilities that Cubesats will need to be precursors for Mars missions in the future, or for exploration, man's exploration in deep space. And because by virtue of being small, lightweight, and made of affordable parts, we can accomplish NASA's future science and exploration missions more affordably with Cubesats. Currently, in the ground tournaments, we have 12 teams registered. 2/3 of those teams are from universities, 1/3 are from small businesses. In Ground Tournament 1, we even had one team that was a high school team. And one of our teams is a single individual retired engineer. So the competition's open to anyone who chooses to enter at no cost to the teams. Our CubeQuest Challenge teams are, we consider them citizen inventors, and we're excited to see how they're pushing the state-of-the-art of these small satellites. And we know that the teams are excited to contribute to NASA's exploration goals for science and for a future journey to Mars. And with that, I'll turn it over to Jitendra.
In order to enable future missions that are robust and sustainable, we need to have a good idea of what our destination looks like. To that end, we developed strategic knowledge gaps, which is more or less a repository of information that you need of your destinations based on what we know today. The next 5 Cubesats I'm going to talk about address these knowledge gaps that we need to find out more about. And let's go to the first one. So behind me you see a solar sail. This is half-size sail which will actually propel a Cubesat to an asteroid. This particular mission is called the Near Earth Asteroid Scout Mission, which will go and do a reconnaissance mission with an asteroid about 100 meters in diameter. While it photographs it, we will get an understanding of what is the surface characterization, what is the morphology. Asteroids have a spin rate, which we need to understand. What is the dust or the debris that it emits out? All these things actually will help us design future human spacecrafts that will afford us a safe mission. So this acts as a precursor scout mission in order to understand and reduce our uncertainty in actually enabling a human mission. The next one, please. One of the biggest problems of deep space human missions that we would encounter is radiation. We haven't gone beyond the low Earth orbit in the last 40 years or more. This particular Cubesat mission, which is called a Biosentinel, and it will be an 18-month-long mission into deep space. It will carry with it genetically modified yeast, just like the baker's yeast you use. And with media, we will activate it periodically and see the effect of the radiation damage, both the solar particles and the galactic cosmic rays. This also carries a miniaturized sensor which not only tells you how much radiation you got hit by, but what kind of radiation. How does that help us? Understanding that radiation damage will help us develop preventive strategies for future human missions to enable safe human spaceflight. Next one, please. You see another lunar mission here, and let me just give you context. My colleague, Mr. Seablum, talked about a lunar mission. We also have had various lunar missions before, the Lunar Reconnaissance Orbiter, the Chandrayaan mission with India, Selene mission with Japan. We had Clementine mission before that. So one would naturally ask, why so many lunar missions? What are you trying to glean through? All those missions had instruments that help us understand the water or the hydroxide characterization. These Cubesats that I'm going to talk about, the one which Dr. Seablum and this one, this is called the Lunar Flashlight, which has actually lasers in a very narrow bandwidth. It will make several passes around the moon and look for volatiles and water species in the cold traps. It will give us a very good map of what the speciation of that water is, whether it is water, ice, whether it is water in a form that we can use. And how it helps us is in a future mission, we have to start living off the land where we go. So it helps us in mapping out sites for in situ resource utilization. Next one, please. We challenged industry and academia, and this was a new way of doing business for NASA through our Next Step broad agency announcement, where we challenged the partners, hey, you do your own internal research and development, and then we will take it with NASA in order to effect a mission. The mission you see here is Lockheed Martin's, through their own internal research and development activities, they developed a Cubesat, which will do a lunar flyby and actually do thermography and surface characterization. After that one lunar flyby, it does maneuvers which will address some of the strategic knowledge gaps that are pertinent to an eventual Mars mission. Next one, please. This is a Lunar Flashlight. It also has, Mike talked of a neutron spectrometer. I earlier mentioned of laser spectroscopy. This has an infrared spectrometer, which is very compact. It's called the Lunar Ice Cube, development activity with Goddard Spaceflight, led by Morehead State University, BUSEC, and Goddard Space Flight Center. This particular infrared spectrometer will actually help delineate the water species, whether it's water, water ice, and make several passes and make us help a composite map. So all these are complementary missions. The missions which we talked about earlier, which went to moon, were sizes of refrigerators. This is one of the compartments where you store vegetables in a refrigerator. So that's the kind of scale with almost a similar capability and delineating more information. Thank you.
Thank you all. We will now open the program for questions. I will rotate questions from those in the room and those on the phone, as well as those submitting questions online using the hashtag AskNASA. For those here on site, please raise your hand and someone with a mic will come to you. Please identify yourself by name and affiliation and indicate to whom your question is directed. And please ask only one question each to allow everyone the opportunity to get their questions answered. First question.
Hi, I'm Josh Barrett with Channel 31 here in Huntsville. My question for you, are you hoping to set a precedent with these 13 Cubesats on later exploration missions? So when they're going further out into asteroids, you could potentially even launch missions out towards those asteroids as well?
Well, I guess we could. You know, these Cubesats don't weigh or don't have a great deal of mass, and we believe we've got sufficient capability to take them wherever we want. Limitations are, right now, we're putting these Cubesats on the Orion stage adapter, which interfaces between the interim cryopropulsion system and the Orion adapter or interface. So that's a nice, easy interface. That goes on a different trajectory than Orion will. We'll separate first and then deploy these Cubesats. We'll take a look at it. One of the great things about this opportunity with EM1 is we are, for the first time, going outside of low Earth orbit. We've deployed Cubesats from ISS and deployed Cubesats from expendable launch vehicles. This is the first time we're actually going beyond low Earth orbit and being able to deploy those. So we look forward to the future and potentially be able to do the same thing as we go further out.
Thank you. Next question. Over here.
Hi, I'm Lee Roop with AL.com here in Huntsville. Thanks for coming to Huntsville to do this. Just to kind of follow up on what Josh asked, you know, if you did do these on future missions, is this something where young scientists can come up with their own ideas for what they would like to experiment on out in deep space, or is this something where future missions would have to, you know, be related to strategic questions that NASA already has?
Well, I think I'll let my colleagues here talk to that as well, but I think the way we approach it, we give opportunities to almost anybody and come up with your own idea. We'll look at the compatibility with the mission, but I'll let you all, Mike.
So NASA actually does that already. We have something called the Cubesat Launch Initiative, where we look for space on spacecrafts that are going to different orbits. And high school students, universities, they develop Cubesats for that. What is different here is we have, over the last couple of years, developed capabilities for communications, for you know, the transponders, the antennae, the gimbal arrays, the propulsion systems here. That is technology people can use now to go into deep space than just a low Earth orbit and a mission of months, maybe. This will afford you years of observation.
So I'd just add to that, yes, we're calling all young folks, so the makers and the dreamers, you know, think about your good ideas. It's perfect to start with this generation, and from high school or beyond, give us your good ideas, and we'll try to maximize all the payloads we can.
Next question.
Scott Johnson with the Spaceflight Insider. I know you have some models over here to one side of the stage. I was just wondering if someone could maybe reference those and explain a little bit more about the deployment of the Cubesats. I mean, what happens mechanically, that sort of thing.
We'll actually be talking about that, exactly that, in more detail in the second part of our program. Any other questions in the room here? All right, we'll conclude our question and answer session for now. We'll have a short video and then we'll continue with the second part of our program.
Good morning. I'm Kim Newton from the Public Affairs Office at NASA's Marshall Space Flight Center. I'd like to welcome everyone to the second part of our program, where you'll learn more about the first flight of the Space Launch System and the 13 payloads selected and how they will launch and deploy. You'll also hear from experts about the Near-Earth Asteroid Project, or NEA Scout, and how this small satellite will reconnaissance an asteroid using a solar cell much like the giant one behind us, and return that data back to scientists here on Earth. I'd like to start out by introducing our briefers today. We have Chris Crumbley to our far left. Chris is the manager of the Spacecraft Payload Integration and Evolution Office for the Space Launch System at Marshall Space Flight Center here in Huntsville, Alabama. Joining Chris is Leslie McNutt. Leslie is the project manager for the NEA Scout project for the Flight Programs and Partnerships Office, also at the Marshall Center here in Huntsville. And next to Leslie is Les Johnson. Les is the solar cell principal investigator for the NEA Scout project located at Marshall also. We'll hear opening remarks from Chris, Leslie, and Les. Then we'll take questions from reporters in the audience. Next, we'll take questions from reporters on the phone. And you can also ask questions using the hashtag AskNASA if you're following us on Twitter. Now I'll turn it over to Chris. Chris?
Thank you, Kim. So 14 months ago, we sent Orion on a test mission on the heaviest launch vehicle, the most powerful launch vehicle that we had at the time, the Delta IV Heavy. That vehicle was able to carry Orion to an orbit of 3,500 miles above the Earth. But now that we have the exploration class vehicle, the Space Launch System, we're actually going to take Orion beyond the moon, 275,000 miles away from the Earth, to a place that we haven't been in years, actually beyond where humans have ever been. And with this capability, we actually have more capacity on this spacecraft, and so engineers were able to say, we can outfit this vehicle and carry more science, more payloads along with us, and that's where we are today. We've been looking forward to this day for some time. We've been working behind the scenes to come up with these Cubesats and to offer these opportunities, and this is unprecedented. To take a Cubesat class payload thousands of miles away from the Earth out into deep space and to actually conduct science. But even with these small payloads, we're starting to pave the way for payloads that are small and large to go on the Space Launch System. So it takes a very large rocket to get that energy to go all the way out to deep space. So the rocket itself, the Space Launch System, is 323 feet tall, about 10 feet shorter than the Saturn V, but 20% more thrust than the Saturn V rocket had with Apollo. And it starts at the bottom with the 4 hydrogen-oxygen engines, the RS-25s. The solid rocket boosters, 5-segment boosters, both of which we derive from the Space Shuttle program to bring to the Space Launch System. A brand new core stage, 220 feet tall, and then hiding behind this cone is an upper stage called the interim cryogenic propulsion stage. And then you see the Orion vehicle, of course, here, the service module, and underneath the shroud, the Orion vehicle. And what connects it is a 5-foot segment called the Orion stage adapter. And in that 5-foot segment, and it's mocked up right here, this is full scale, this is what you would see if you were standing inside the Orion stage adapter. 5 feet tall, 18 feet in diameter. And this is a full-scale deployer of the Cubesats. And you can see in the model, we had room within the Orion stage adapter to put 13 of these Cubesats in, and then 1 extra spot for the avionics deployer. And that's what we're going to be taking up into the deep space. Now, this is the second of the Orion stage adapters, actually built right here at the Marshall Space Flight Center about 3 blocks away. So the first one flew on EFT-1 14 months ago, connecting Orion to the Delta IV launch vehicle. So this vehicle and everything that you're seeing here, things that we're starting to produce right here. But I want to talk to you a little bit about the Exploration Mission 1. And I think we have a short video that we can show and depict what that looks like. So the vehicle blasts off, all 4 engines with the solid rocket boosters. The boosters, as they did on shuttle, burn for about 2.5 minutes. Then they'll separate. The core stage carries the entire vehicle on up into orbit. As main engine cutoff, the spacecraft will depart, and then the interim cryogenic propulsion stage will light its RL-10 engine, sending the spacecraft on into deep space on towards the moon. About 11 minutes later, the engine will cut off. We'll let Orion know that it's safe to separate. They will separate on their own power, and about 30 minutes later, we will start doing a disposal burn with the upper stage. Once it gets to a safe distance, then the avionics deployer will turn on, and it will start deploying each of these Cubesats one at a time with a little spring ejection system to come outside of the system. And you're seeing right now where the Cubesats are inside the spacecraft. Once these systems deploy, they get a safe distance away from each other and from the upper stage. Some of them will turn on some novel propulsion like solar cells, like you see behind me, and you'll hear more about. Some of these will go around the moon. One will actually go to an asteroid, and others will be studying the environment around deep space. But we have worked in this field for several years. The Marshall Space Flight Center has been leaders in working with science and technology payloads and taking those up on the space shuttle and the space station. And the Space Launch System program asked some experts in the field, our Flight Programs and Partnerships Office, to integrate this for us. And they've been doing so. So I'm going to introduce you to Leslie McNutt, who is one of those experts. She's the project manager for NEA Scout, and she's going to tell you more about her mission. Leslie.
Thanks, Chris. So Near-Earth Asteroid Scout, or NEA Scout, one of the 13 payloads that are hitching a ride on SLS. So NEA Scout, just like you've heard, is a 6U CubeSat. It's about the size of a large shoebox and will weigh no more than 30 pounds. So within that constraint is a fully functioning spacecraft. It's pretty incredible. And so you can imagine volume and mass are quite precious in that small area. So it's the most complicated game of Tetris you've ever played, but a whole lot of fun for the team. So NEA Scout's going to give you both science and technology objectives. For science, we're going to image an asteroid, specifically 1991 VG. We're going to go by close enough, within about 1 kilometer, and slow enough to see a whole rotation of that asteroid. We're going to learn a lot about it. We're going to be able to fill in some of those gaps that scientists have about asteroids, and then that will be applicable to future missions to asteroids for really any number of things, including human exploration. The next thing that NEA Scout's going to do is show you a whole new exploration platform. It's a reconnaissance platform with its first target being an asteroid. That platform is enabled by our propulsion, the solar sail. So behind me you see a half-scale solar sail. So our flight unit is going to be twice this size. So why are we in this facility, you might ask? This is the flat floor facility, and as you might imagine, the solar sail is not designed to deploy in Earth's gravity, so how could we test that out? On the flat floor, we were able to use air-bearing technology, kind of like a puck on an air hockey table. So as we deployed the solar sail, it could just glide across the floor, and we could check out exactly how that deployment would work. Because this is a pretty big sail. The sail that we're trying to build, twice this size, we really need to figure out how best to make that deployment work. So 36 square meters, that's what's behind me. The flight unit will be 86 square meters, and it's all going to fold up onto this spool. So that's pretty incredible, right? So to tell you more about the solar sail and how it's going to function is Les Johnson. He is the principal investigator for NEA Scout solar sails.
Thanks, Leslie. Yeah, the NEA Scout is going to give us and demonstrate a new capability for exploration, and it's going to be low-cost reconnaissance of an asteroid. And why that's important is because someday we're going to want to send people to asteroids, and it's a good idea to get a lay of the land shot before you get there with people, as Jitendra explained earlier. We want to know more about the target, what it looks like, what is its spin rate, does it have dust around it, and the sail is going to provide the propulsion system to let us do that. Coming up on your screen is an animation of the mission sequence, and I'll walk you through what happens as NEA Scout goes to its target. The first thing that will happen is we'll be among the 13 payloads that are ejected, and our small CubeSat will be deployed. As it moves away from the SLS, it'll go toward the moon and deploy its solar panels so we can generate power and call home and give a status check of all the systems on board the spacecraft before we begin our actual mission. After we've been around the moon, we're going to deploy the solar sail. We'll do that by deploying 4 24-foot booms, which will pull out the sail, which will be a larger version of what you see here behind us. and that will provide the propulsion system that will take NEA Scout to the asteroid. We'll then do another lunar flyby, get a little bit of a gravity kick from the moon to send us on our trajectory. Well, one of the questions people have is, well, how does a solar sail work? Well, a solar sail doesn't use wind, it uses sunlight. And this is a piece of the kind of the sail that we're going to be flying. It's about 2.5 microns thick. That's about the thickness of a human hair. It's a plastic, it's got aluminum on it to give it lots of light reflectivity. And what happens is, as you're in space and you unfurl this, the light reflects from the sail, and even though light doesn't have rest mass, it does have momentum. So imagine light, particles of light, photons, as being like little ping pong balls bouncing off of this, and together they impart a little bit of their momentum, and the sail will recoil and move. We steer by tipping and tilting the sail and changing the angle with which the light reflects from the sail. What that does is it changes the net direction of the force or the thrust that allows us to steer the sail in the direction that we want to go. Now, this force is a very small force. It's much less than an ounce per football field. You would never notice it. You can't feel this pressure. But as long as the sun is shining and our sail is deployed near the sun, we're going to get constant acceleration from that. Leslie mentioned that mass is king here. The key to this is a lightweight, low-cost spacecraft. Now, when we get near the asteroid, we have a camera on board. We're going to image the asteroid. We're going to cover about 85% of its surface. We're going to send that data back home, understand more about what this future target is, and demonstrate this capability that could be used to visit many asteroids relatively inexpensively. So you put it all together, and Exploration Mission 1 is going to give us an integrated capability in the proving ground to take the Orion capsule, the Space Launch System, and demonstrate its capabilities. And along for the ride will be a new capability for low-cost interplanetary science and exploration by deploying these Cubesats. In the future, solar sails could be made much larger to do other science missions. They have the potential to study the sun and to go to vantage points that are currently impossible with other propulsion systems. So I see a bright future, no pun intended, for solar sails as this first flight for the United States into interplanetary space with our largest solar sail ever.
Thank you, Les. Thank you, everyone. Now we'll take questions from reporters here in the audience, and then we'll take questions from reporters on the phone. If you're on the phone, please hit *1 so that you can be entered in the Q&A queue, and then we'll go to social. So please limit your questions to one at this time, and please announce your name and media affiliation. So we'll start here in the room. Josh.
Hi, Josh Barrett again. My question is one of your goals going to be identifying candidates for the proposed asteroid redirect mission?
You want to take that?
Really, our goal is we've got this one target asteroid, to learn what we can about that asteroid. Now, that's the thing. There's a lot of things that scientists don't know about asteroids, so based on information gleaned from this mission, it could potentially affect the missions you then choose after this mission.
Yeah, we're not going to be in time to affect the decision, I think, for the asteroid redirect mission, but for future missions, it's a possibility.
Any other questions? Lee, right here.
Hi, Lee Roop with AL.com again. Just looking at your sail and the way you pulled it out there, Les, it looks kind of flimsy, little thin. How strong is it, and what happens if something pokes a hole in it?
Well, this material is very lightweight, and that's one of the revolutions that allows NEA Scout to happen. This is a polyimide. It's called CP1. It's very lightweight, but it's pretty robust. I mean, I could damage it if I wanted to tear it, but just handling won't damage it. And there is no doubt that when we're in deep space, we're going to get hit by micrometeors. It's going to happen. But the thing is, it's so thin and they're traveling so fast, when they hit it, they're going to poke just a little teeny tiny hole in it and not deposit much energy. The same micrometeorite hitting a block of aluminum would stop and deposit all of its energy of motion. It would be like an explosion and be a lot of damage. But for us, it'll just poke a little pinhole. And in the off chance that we get a tear, we're like a parachute. We have ripstop. And so if there is a tear, the ripstop should stop it before it gets too big.
Okay, any other questions? All right, let's go to social media.
Thank you, Christopher Lair, NASA Marshall Space Flight Center here. And one of our questions online is from Jay Rake at Young. Jay Rake asked, what materials or support will or does NASA supply each CubeSat team?
So, well, I'll let Chris talk about any integration type support. At least we're a team that is NASA funded. So supported by HEO and AES, so we get that sort of support from NASA. I know that from SLS, we get a large amount of support as far as requirements from the vehicle and integration needs, and so we talk daily with those individuals to help us on the path to the vehicle.
So each one of the groups, the mission directorates put out their own call, and then they self-fund each of those. And they're funded at different levels. But what Mr. Gerstenmaier and Mr. Hill have offered is that we will cover the integration cost of putting it onto the vehicle. So we built in-house the apparatus to hold the deployer, and we ask every one of the units to use the same deployer so that we can be consistent on this first flight.
Okay, any other questions in the room? All right. This concludes today's second part of the program. If you would like to learn more about SLS, Orion, or NeoScout, visit www.nasa.gov, or you can see the URL that'll come up on your screen for the materials that we have today. And thank you for joining us.